Okay, Year 12, last video of the course. And what we're aiming to do is just that that environmental impacts of synthesis. Okay, so I've just chosen a couple of examples to talk about in a little bit more detail. So as first you can see is acid rain. So acid rain occurs when the gas sulfur dioxide and also nitrogen oxide, so those gaseous emissions, are dissolved into water droplets in the atmosphere. And so when precipitation occurs, it has low concentrations of sulfuric acid and nitric acids. Okay? So sources for these. It's true that sulfur dioxide is given out by volcanoes, and there are a couple of little sources there for nitrogen oxides, tiny small amounts, but it's mainly humans. Okay, so the main source is burning of coal. Okay, so that's usually electricity production, and also other fossil fuels such as like a burning of petroleum and diesel and stuff like that are producing sulfur dioxides because they have small amounts of sulfur in them, and also heating, high temperature internal combustion engines that get nitrogen from the atmosphere in there also produce nitrogen oxides. Okay, so any power generations, engines, vehicles, that type of thing are all sources for nitrogen oxide as sulfur dioxide. And so this image I pulled up from the US EPA. It's quite a good image here to show the cycle of it. Okay, let's see if we can follow it. So I've got nitrogen oxides, so they're often summarized as NOx because you can have NO, NO2, N2O4, all different types. So we just summarize them by calling them NO subscript X, or sometimes us chemists call it NOxes. Excuse me. And actually, we also use SO2, and there can be other sulfur oxygen compounds. We call them SOXes. Anyway, it's like the beginning of a Dr. Seuss book, isn't it? So, nitrogen oxides, sulfur dioxides, coming from these sources such as engines, trucks, and power generation going up into the atmosphere. Mixing with water in clouds, so the small droplets. So what does it say? The pollutants are transformed into acid particles, so you get a reaction with the water and these gases. They're acidic oxides, so we're producing acidic water, so we're lowering the pH of those. And we get with different pressure changes and different densities, we're getting different precipitations. So over here, I don't know what that is, but that looks like rain, and then we're getting snow, all of them acidic, and then it may cause harmful effects in soils, streams, and lakes. Okay, more on that in the next slide. Okay, the impacts of acid rain. I've just chosen the main ones here. There are a few more, and you can go more into depth here, but these are the main ones summarized. Okay, so acid rain will lower the pH of aquatic environments. Okay, so anything with water, it's changing the pH, lowering them. Different species of animals, plants, bacteria, algae, all the various forms of life have pH tolerances. Okay, some of them can be quite narrow too. Some of them can be a bit more wiggle room. What's the technical word for that? So yeah, you're changing the pH of the environment, of the aquatic environment. You're changing what species can survive there, and can they adapt quick enough, and can other species move there? Probably not. They're getting killed. Okay, so that relates to this little diagram here. We've got different animals and their critical pH level. I don't know what critical means. Can they go below that or above that, or is that where they should be? But anyway, you get an idea that there's a range of different happy places for different animals. Okay, acid will oxidize metal deposits in the ground, leaving more metal ions in aquatic environments. Okay, so it's going to dissolve those metals more, and so they're getting into aquatic environments, and some of the concentrations of these ions will reach toxic level for some of these aquatic species. Okay, so you're increasing the amount of dissolved metals in your aquatic environments. Acids will leach soil nutrients away from plants, so acids will explains it all. Acid rain will also damage the leaf surface, so biology people will need to help me out here. But usually there's a slight wax coating on leaves to protect it, basically, and you can get very waxy ones depending on the environment that it's from. Or isn't it the more waxy they come from drier environments and they need to keep the water inside? Anyway, this waxy coating has a various different functions, like keeping water in, protecting it from outside stuff. The acid's going to chew away at that layer, and you're going to get more dead leaves and less solar gathering, less solar panels basically for the plant. More likely it is to get hardship and die. And also this one relates to it too, acidic fog and clouds. So floating around small droplets, or aerosols we call them, sitting on tree foliage will strip the nutrients away from them too. So strip the nutrients from the leaves and stuff. Acid rain runoff will damage the whole buffer systems in waterways. So we've got natural buffer systems in waterways, such as the bicarbonate one that we've been talking about. And that just comes from the dissolving of rocks up in mountains as rivers pass by. So that's really good. But too much acid in there and it's going to exceed the buffer capacity and ruin the buffer. Okay. I put this low down the list. Yes, it causes corrosion on human infrastructure, but we're the ones who do it and we're the problem, so no point whinging about it. That's low on the priority. And also acidic microdroplets of water. So for human health, we've done a bit of research. So they're lung irritants and to all respiring species, okay? So to anything with lungs. So we've done... studies have linked acid rain areas to increase incidence of asthma and heart disease in humans. And of course that will relate to other animals that respire as well. Okay, so that's a good overview. Keep that in your back pocket in case you need to talk about one of the impacts of synthesis reactions, production of acid rain. That's a good one. So what is it? What are the sources of it? What are the impacts of it? Okay? All right, another thing I thought I'd add in here is a movement in chemistry that's been going on for a while, but it's been more formalized in the last 10 years or so, is this concept called green chemistry. And I know you might call it lazy, but I've just gone to the great old Compound Interest. They've got a great summary of it. They do great summaries of everything. So let's have a quick read and choose a couple of these out so that if we do get a question about green chemistry or the impact on stuff and what we should do to get around the impact of using negative synthesis kind of techniques, you could bring up green chemistry. Okay, so it's an approach to chemistry that aims to maximize efficiency and minimize hazardous effects on human health and the environment. Okay, so we realize that it cannot be perfectly green, but these are like goals of ours. Okay, but the overall negative impact of chemistry research and chemistry can be reduced by implementing what we've decided on is these 12 principles. Okay, whenever possible. Not all of these are easy to understand, but some are quite obvious, okay, that we can talk about. So, like number 1, waste prevention. We want to prioritize the prevention of waste. Rather than cleaning up and treating waste after it's been created, prevent it being made, okay? So, going into planning. All right, less hazardous chemical synthesis. So designing chemical reactions and synthetic routes, remember, we can choose various ones, that are safe as possible. So consider the hazards of all substances being handled and including waste, okay? And choosing alternative pathways to get what you want, to avoid stuff that's going to be horrible for health or the environment, okay? Not always possible, but it's a principle that we tend to stick by. Number 9 there, catalysts. Okay, instead the use of catalysts, because catalysts you don't need much, and remember it's not consumed in the reaction, it just helps the reaction take part. You just need a little bit, so it often saves us a lot of work by using a good catalyst. And you'll notice too that catalysts work, I mean enzymes, biology does it really really well, but there's the catalyst work in chemistry in the last say 5 or 10 years is really kind of at the forefront, because we're all kind of leaning on these green chemistry principles and trying to save a lot of research resources and waste and stuff like that. I think at least half of the Nobel Prizes in chemistry have all been to do with catalysis in the last 10 years. Watch people show me that I'm wrong though, but it's very important, okay? Alright, so design for overall energy efficiency, number 6 here is good. So we need to choose the least energy intensive chemical route in our design. So we if we can, we need to avoid heating or cooling, because that's all transfers of energy, and as well as pressurized or high pressure or low pressure, okay? So you want to get ambient temperature and pressure as much as possible, if you can, okay? If it's viable, we'll aim for that. Real-time pollution prevention, so real-time monitoring of our emissions is very helpful to avoid all various types of pollution. All right, I think I'll leave it there. You can read through the rest of them, but they kind of make sense. Instead of remembering all 12, pull out 3 or 4 maybe stick to 3 that you can keep as an idea there in case you get one of these questions in your exam, okay? Can you explain it? One more that I thought I'd add in there is this green polymer chemistry movement. Now this has come about, I think I talked about it in the polymer chapter. So there's all these natural polymers that we can use and make. But what ends up happening is one of the problems is these so-called biodegradable plastics just break down into microplastics, where they can do more harm to living things than before. So there's a lot of problems around the polymers that are so-called natural and stuff like that. But here with this green polymer chemistry movement, they were approaching it with a slightly different way, okay? So their movement, the movement aims to produce the polymers that are very commonly used now, okay? That could there could be some negatives, but they've got some ways around it. So like stuff like polyethylene, polypropylene, PVC, PET, polyamides, the stuff that we're using already, and we're using them very well because they're strong, they're flexible, and stuff like that, okay? So instead of making these other plant-based ones, we're using ones that we want to use anyway for their strength, but we're getting them from plants as well, okay? We're doing some extra reactions there to get them from plants. Okay, and also it's coupled in with a very strong recycling program, and that's a big ask at the moment. We do terrible with plastic recycling. So it's using new ideas and new reactions and new processes to get those polymers that are really strong, that we have been using but getting from fossil fuel industry, getting them from plants instead, and really backing it up with a strong recycling program, okay? So there's a lot of chemistry, there's a lot of biology too here, because we're talking about using genetically modified yeast, algae and bacteria to produce these monomer materials, these monomer precursors, so stuff that we can get these good monomers from and then just do little reactions to it to optimize the properties of the polymers, okay? It is being invested in an awful lot and developed widely, and you can look up that article too. I don't know if you want my opinion here. It's very pie in the sky. It's a great idea, but it's just practicality on a worldwide scale. Oh, I've got a lot of doubts. I mean, we can't even get a good recycling system going for plastics. Anyway, that's the end of the course, really. I've just got that last worksheet for you, and there's some you should knows. Yeah. Done. Tick.